Question 14. A loudspeaker emits a constant frequency of 2,500 Hz and is swung in a horizontal circle at a speed of 5 meters per second. A stationary observer far from the speaker hears a maximum frequency of 2,537 Hz when the speaker is moving directly toward them. Determine the speed of sound in air. This problem tests our understanding of the Doppler effect for a moving source and stationary observer. Let's recall what we know. The Doppler effect describes the change in observed frequency when there is relative motion between a source and an observer. When the source and observer move relative to each other, the sound waves are either compressed or stretched. For a moving source and a stationary observer, the observed frequency increases when the source moves toward the observer and decreases when it moves away. This happens because the sound waves are compressed in front of the moving source. The Doppler formula for a moving source and a stationary observer relates the observed frequency to the source frequency and the speed of sound as follows. Now let's work through the solution step by step. First, we list the quantities given in the question. The source frequency is 2,500 Hz. The speed of the sound source is 5 meters per second. The maximum observed frequency heard by the observer is 2,537 Hz. Next, we recall the Doppler effect formula for a moving source and a stationary observer. The observed frequency equals the source frequency multiplied by the speed of sound divided by the speed of sound minus the speed of the source. Since the maximum frequency occurs when the source is moving directly toward the observer, we use this formula with the given values. So we substitute the numbers into the equation. The observed frequency is 2,537, the source frequency is 2,500, and the source speed is 5 meters per second. This gives the equation 2,537 equals 2,500 multiplied by v divided by v minus 5, where v represents the speed of sound. To simplify the equation, we divide both sides by 2,500. This gives 2,537 divided by 2,500 equals v divided by v minus 5. Carrying out the division gives approximately 1.0148 equals v divided by v minus 5. Next, we solve this equation for v. We multiply both sides by the denominator, v minus 5, to remove the fraction. This gives 1.0148 multiplied by v minus 5 equals v. Now we expand the bracket. Multiplying 1.0148 by v gives 1.0148v, and multiplying 1.0148 by negative 5 gives minus 5.074. So the equation becomes 1.0148v minus 5.074 equals v. Next, we collect the terms involving v on one side of the equation. Subtracting v from both sides gives 1.0148v minus v equals 5.074. This simplifies to 0.0148v equals 5.074. Now we solve for v by dividing both sides by 0.0148. So v equals 5.074 divided by 0.0148. Carrying out the calculation gives approximately 342.84 meters per second. Rounding this appropriately gives a speed of sound of about 343 meters per second. This is our final answer. What did we do? We began by identifying that the maximum observed frequency occurs when the sound source is moving directly toward the observer. Then we used the Doppler effect formula for a moving source and stationary observer, and substituted the given frequencies and the source speed. After forming the equation, we rearranged it algebraically to solve for the speed of sound. Finally, we evaluated the expression to obtain a value of approximately 343 meters per second. To summarize the key ideas from this problem, when a sound source moves toward an observer, the observed frequency increases, and when it moves away, the observed frequency decreases. The maximum observed frequency occurs when the source is moving directly toward the observer, while the minimum frequency occurs when it moves directly away. Since this was a case of the Doppler effect involving a circular path, there are directions that mediate between directly toward and directly away from the observer. For a moving source and a stationary observer, The Doppler effect equation relates the observed frequency to the source frequency using the speed of sound and the speed of the source. The formula has plus or minus in the denominator to use for either of the cases of the source moving toward or away from the observer.